like this, remember that logarithms hate radicals. Logarithms and radicals are not friends. They do not like each other. Logarithms and exponents are friends. So whenever we get radicals, we're going to re-express as an exponent. So that's 5.81 times 7.11, and they're both to the 1/2 power. Okay? So now that we've got that, all they want us to do is to evaluate that using log. So we take the log of that, and so that's log of that gives us 1/2 times the log of 5.81 plus the log of 7.11, 1/2 log of 7.11, 71.1, excuse me. And again, like I kind of said in the podcast, this was useful because before we had calculators, which is, yes, all the way back in like the 1960s, so 50 years ago, not even 40 years ago, calculators were just starting to become mainstream. But before we had the calculator, I could just put that in my calculator and punch a button and have it all come out. This is the way we'd have to solve this, because we have tables of logs and slide rules. And with that, we could look up the log of 5.81, multiply that by 1/2, log of 71.1, multiply that by 1/2, and then reinstate that with 10 to the power to find the, do the inverse function again. To take the log of it, we'd have to invert it back, but we could actually do this with tables and a slide rule. That's how we'd handle that. Yes?
I was just kind of confused because I didn't know how to do this, so I tried 29, but
Mm-hmm.
the same way that you did it up there. But I didn't get the same answer that was in the book.
29.
So you just do log
50, log 754 plus log 24.5 plus log 0.00128.
That's what I did, and I didn't get 230.
No, because that's the log of that. Then you have to take 10 to that, whatever that answer is, you have to take 10 to that power.
I don't know why, but it didn't, like, in the back, it doesn't, for 29, it's 236.5.
Yeah. Well, let me try this for a second. Log of 754, parentheses, plus log 24.5, parentheses, plus log of 0.0. Oh, shoot. It didn't let me keep my answer. It was 2.36 something. Yeah, it works. If you take the log of all three of these, I mean, when I take this, I have to take half the log of 5.81, okay? So I take 0.5 times log 5.81. I have to make sure I close the parentheses. And then plus 0.5 times log of 71.1, close the parentheses, and that's going to give me 1.308. 0.80222867. It gives me a pretty long number. And we don't want to round this a lot, because in order to find my answer, I have to take now 10 to that power. So if I take 10 to the power of 1.308022867, I get 20.32. 10 to that power is 20.32, which is the answer that we're looking for. 20.3 they got, yeah. So you got to remember, it's not an equation. I'm not taking a log of both sides, so it doesn't balance. So it's basically, it's like I'm diluting it and then I'm rehydrating it. Think of it that way. That's the way I kind of think of this sometimes when I have to take the log of it. It's like I'm diluting it, I'm dehydrating it, I'm taking all the moisture out of it, and then transporting it easily because it's light, now it's dehydrated, and then to reconstitute, I got to add water to it again. There's a word picture for you. Yeah.
Can you do number 22 on 632?
Sure. Uh, 4.4 times 10 to the 7th power? Sure.
No, it's
630.
maybe I'm sorry, I missed the next page. 639.
Okay. X is less than log of 52.7?
Yes.
Or log base, what is it, log base 3?
Yes.
Oh. I think you overthought this one probably. 52.7 it was?
Yes.
Okay. And it's less than, not that. Equals to. All we do is change base here. That's log or ln of 52.7 divided by the log of 3. And all you need to do is put that in your calculator and simplify it.
Okay, and number 18 on that same page.
Sure.
It's very similar. When you're dividing by a log, do you have to switch the greater than less than sign it off?
Only if you multiply or divide through by a negative. Same as normal. The biggest thing to be careful of here when you're doing this in your calculator, because the calculator error comes in really quickly, is a lot of people don't close their parentheses. So they get log of 52.7 over log 3 is what they enter in their calculator. That's not right. Okay? That's not going to work. If you don't close your parentheses after this before hitting your division sign, you're going to wind up doing this, which is not what you want. That's not going to be pretty. So watch that. So make sure you're closing your parentheses when you're working with logs in your calculator. And honestly, you know the way the calculator does all your square roots and all your stuff like that, how it actually, the internal processor works to calculate those values, is it uses logs. So when you're doing in your calculator 352.7 times 262.6 times the square root of 18, the calculator in the processor, how it's actually figuring that out, is all with logs. That's how it does it. That's how the programming inside your calculator works. Why? Because that's how it was done when people started programming calculators, and they just keep doing it with logs. Yeah. 24 on that page. X to the 2/3 is greater than or equal to 27.6. X to the 2/3 is greater than or equal to what, 27.6? Okay. Take the log of both sides of the equation. Log of X to the 2/3 is greater than or equal to the log of 27.6. Okay. The 2/3 comes down as a coefficient, so 2/3 log X is greater than or equal to log of 27.6. So multiply both sides by 3/2. So log of X equals log of 27.6 times 3/2, which I can get. So I take the log of 27.6 parentheses times 1.5 3/2. Gives me 2.161. .16136. Okay? Sorry, log X. That was supposed to be X. Okay. Now, I need to find X, so I do the inverse function of log, which is 10 to the X power. So I take 10 to both these powers. 10 to the log X just equals X is 10 to the 2.16136 power. So 10 to the 2.16136 power gives me 145, essentially. 144.997. And that should be my answer. Which number was this? Yes, 145. I'm sorry. I lost my inequality. I have a tendency to do that. I always have to double check that. X is greater than or equal to 145. Okay? Again, logs are really useful when we have a variable in the exponent or we are solving for a difficult exponent. We have something like x to the 2/3 power. I mean, really, the other way of dealing with this is saying that this is the cube root of x squared is greater than or equal to 27.6. I mean, really, we could have done this the old-fashioned way as well, probably pretty easily, by cubing both sides. X squared is greater than or equal to 27.6 squared, and taking the square root of both sides. So x is greater than or equal to the square root of 27.6 cubed. So either way works, actually. One way we use logs, one way we use radicals. And if I put that in my calculator just to see, 27.6, the square root 27.6 to the third power. Yep, exactly the same answer. I mean, 144.998 because of a slight rounding error. Yes. Number 26. 5 to the x minus 1 equals 2 to the x. Ah, classic. We could take the log or the natural log of both sides. Now remember, we're taking the log of both sides of the equation. I can take the log, which is a log base 10, or I could use the natural log ln, which is log base c. I don't have to take the log. In fact, a lot of people wind up doing ln because it's less letters to write. And it makes absolutely no difference in how we solve the problem. So let's do this one natural log instead of log base 10, because there's no reason to prefer one over the other. So I take the natural log of 5 to the x minus 1 equals the natural log of 2 to the x. Exponents become coefficients. So I get x minus 1 times natural log of 5 equals x times the natural log of 2. I want to get the x's by themselves on one side, but that's going to be a little difficult without distributing. So I get x ln 5 minus 1 ln 5 equals x ln 2. I can swap these two, subtract the x ln 2 from both sides, subtract the 1, add the 1 ln 5 to both sides. I get x ln 5 minus x ln 2 equals ln 5, positive 1 ln 5. Factor out my x. Now my x is going to be by itself, so x equals the natural log of 5 over ln 5 minus ln 2. And no, I can't cancel the ln 5s. That doesn't work. And like I say, you could do it with log, it doesn't matter, instead of ln, log base 10 or log base e. But ln 5 parentheses divided by, better add some parentheses, ln 5 parentheses minus ln 2 parentheses, and the second parentheses, 1.756. So there we are. So whenever we get those variables in exponents, we bring those down as coefficients. A lot of times we do have to wind up distributing like this, rearranging so the x's all come to one side, then factoring out the x's, and we get a little log thing that needs to be solved, but most of that's done in our calculator. Very classic log equation. So what's the difference again, just for fun? What's the difference? Why do we have two functions? Log is log base what? 10. Okay? This really means log base 10. What is natural log? Is really log base E, the natural base, Euler's number. That's the difference. It's just a different base. I mean, I could run log base. I mean, I could run this with this equation with log base 6 if I wanted to. It doesn't matter which base I put my log in to run something like this. It really doesn't. But I generally don't have log base 6 in my calculator, which would make it really inconvenient. But that's the big difference. Log 10 versus ln. All the rules are identical, the same for natural log as they are for regular log. And really, that's what today's lesson is. When do we tend to use natural log? Whenever we want. But definitely if I have something with an exponential base. If I have an e to the power function, I'm always going to use natural log on that, not log base 10. Why? This gets us into today. It's a nice segue to today's lesson. Because if I have e to the x power equals 5 or something like that, what happens if I take the natural log of both sides? Ln of e to the x equals the ln of 5. Now, you may say, well, okay, but that's really not saving that much. By definition, the natural log of e to any power, this power is going to come down and become a coefficient, right? And the natural log of e, by definition, equals 1. Just like the log, log, of 10 equals 1. That's why we use logs when we're dealing with scientific notation. If I have 3.14 times 10 to the 8th power, and I take the log of that, that's the log of 3.14 plus the log of 10 to the 8th power. The log of 10 to the 8th, that just equals 8. Because log base 10 of 10 to the 8th. So using logs of scientific notation is kind of a no-brainer. The only thing I really have to look up is the log of the 3.14 here. That's why we use scientific notation a lot in science. Again, it goes back to logs. That's why scientific notation exists, because it works with logs so easily. Because I don't have to calculate this. I don't have to look that one up in a table or use a slide rule. I can just do it this way. So if I'm solving natural logs, a lot of this is going to be really simple. Find the natural log of 61.3, the natural log of 1. That's just punching numbers in your calculator, right? Getting on my calculator, ln 61.3. Try again. 4.11. 5, 6, let's go. Ln of 1, punch in my calculator, ln of 1 is 0. Anti-ln means e to the 0.053 power. That's the anti-natural log. Like the anti-log is 10 to a power, the anti-ln is e to the power. So that means e to the 0.053 power. It's a second function ln button on your calculator. 0.053 is 1.05. This would be e to the 4.32 power. .12. So natural logs really work exactly the same as regular logs. The techniques we use are exactly the same. There's no new formulas. The only time we do anything special with natural log, where we really need to use natural log, is where we have an exponential function with a base of e. We always have the option of using natural log whenever we want. I don't know why things are bleeping, but they are. Oh, mail for Bridget and Carson and Jessica and Nikki with the wrong name and Jacob and Jenna, who's not here. Is Jenna testing today, or is she? Yeah. Are you going to see her? You don't know if you're going to see her?
I don't know, but I'll get it.
Okay. It's the same note. All right, so let's take a look at just a couple things we have to go over today. If I have ln 4.2 equals ln e to the 0.32x. Again, don't overthink these. They're really pretty simple. ln e to any power. Okay, just a quick reminder. ln of e to any power just equals that power. Okay? Whenever we see the ln of e to something, that's like a golden ticket to free easy time. So if I see this, ln of 4.2 equals ln of 3.32x, I get the ln of 4.2 equals 0.32x. I divide both sides by 0.32, and I've got x. It's really that simple. That's all you have to do. Here I have an exponential function. Again, just as normal, I try to get my exponential base by itself. 12 equals 6 to the e times e to the 2x power. I divide by 6 first, so I get 2 equals e to the 2x. So I don't have to deal with all that multiplication stuff. I just get I isolate my exponential. I take the natural log of both sides. I could take the log of both sides technically, but the natural log can be easier because ln 2 now just equals 2x. So x is the natural log of 2 divided by 2. So it really just kind of sails right through. Could I have done that with log? Yeah, I could have. It would have been messier. But I could take the log base 10 of e. I just don't know why I'd want to when I could take the log base e of e, which is 1. So it really makes life easier. Really the big thing with natural logs are the applications. Exponential growth and decay, continuously compounded interest, problems like that. The applications in science and business and that sort of thing are all over the place. And really, science and business, if you're going to study science and business at all, you're going to use exponential functions with a base of e. And so you'll use natural logarithms to solve things. A very common function for exponential growth, which is often modified and tweaked and all sorts of things, is this y equals ne to the kt power. If k is positive, k is a constant of growth. It might be an interest rate or some other constant of growth. If k is positive, it's growth. If k is negative, it's decay. So have you ever looked at like radioactive substance, radioactive decay in half-life of elements? If k is negative, it's a decay function. If k is positive, it's a growth function. T is a time unit measurement, usually of some sort. E is Euler's number. N is usually the initial amount of whatever we started with, or whatever we're measuring. N, or Y, is the final amount after that given time t. Y is given as a function of t, essentially here. N is the initial amount. And we use this in all sorts of different science and business functions, the same basic formula. Say, study future needs of the city. Sewage can support 250,000 residents. Current population is 175, up from 106,000 10 years ago. Assuming the population continues to grow at this rate, when will the sewage system need to be updated? How many people will the new system have to accommodate for the system to last 15 years before needing to be updated again? Want to study engineering, a little civil engineering? Exactly the kind of problem you'll be doing. Very common. A little overly simplified, but gets the idea. So, first we have to figure out what's the rate. What's the rate of growth? Obviously, our city is growing. It went from 106,000 10 years ago to 175,000 now. So, if we're at 175,000 now, we're at 106,000 10 years ago times E to the K, which is unknown, times 10K. So I'm going to divide through, to find the constant, I'm going to have to divide through by the 106,000. Thousands cancel off to reduce that. So 175 divided by 106 equals e to the 10K. So 175 divided by 106. That's 1.65 equals e to the 10K, natural log of each side. Yay, natural log of e to a power, this is 10K. So I take the natural log of 1.65, parentheses, then divide by 10. And I get k is 0.0500. There, I've got my constant of growth now. Approximately 5% per year. There's my constant of growth. Now I need to know how big is, how many people would you need to accommodate 15 years in the future? Well, my current population is 175,000. Times E, now I know my constant is 0.05 times 15 years. So 175,000 times E to the 0.05 times 15. Or I need to build a sewer system that will accommodate a population of 370,475. So if I build my sewer system to accommodate that many residents, I should be good for 15 more years before it needs to be updated again. So what we do, we found the constant of growth, and we just substituted it into my equation again, went back to that same equation all over again. So there you are, you future engineers.
So we didn't even use 250.
Nope.
So that's just
That's just a number there that's to show you that it's actually still functional. We don't need to do that. I mean, I guess we need to build a system, if we want to say I need a system that can accommodate another 120,475 people, and to expand it by that much. So that would actually be my actual expansion. So I guess we would use it in that effect. We need to expand it by another 120,000 or so. But not in these two formulas. I guess I worked it out step by step here. So there you go. But we just did it in one page, and that's it. So if you want the step-by-step, one slide at a time instructions, they're there as well. But other than that, the natural log functions work the same as the regular log functions. Is why I knew we didn't have a lot to do today, because it's the same thing. It's just using a different base. But let's keep practicing working with our logs. I know a lot of you probably didn't get a lot of homework done this weekend. Big weekend for a lot of people, right? Yeah, lots of fun. Hope you had a good time. But back to the work now. Tomorrow is strictly review. Please come with lots of questions. And yes, I'll put the homework up. There it is. 14 through 30 even and 31 through 36. Let me double check that. See if I want to modify that at all. Yeah, 14 through 30 even are really quick little problems. They're very short. And then 31 through 36. I don't think I want to do all of those. That's a lot. Let's do 31 and 32. And what would you rather do? Ecology, sales, finance, or meteorology? Meteorology? Okay, 36. So 31, 32, and 36. I'm going to lighten that up for you. 31, 32, 36. I took off half the story problems. Anyone going to complain? No? Make sure you talk to the people who are AP testing and stuff today, that they know about the change assignment, because that's not necessarily going to be on the website. Or if you want to make them suffer, don't tell them. And then we can laugh at them. And like I said, if you are AP testing at some point during this week, good luck on your AP test. Work hard. Do great. And when you come back, we'll just make up whatever you missed. If you missed your quiz or a test, I will try to get in the test center for you so you can take it at your earliest convenience. Okay? And we're just going to keep plodding along. And the good news of today is the 7th. So we have Monday the 4th. Oh, I'm sorry, it's not the 7th. Wrong month. I'm still on April over there. Wow, I never switched my calendar. Today's the 5th. 1, 2, 3 more Mondays. 3 more Mondays, folks. You'll have to have come to school. Yeah. 3 more Mondays, and one of them is a late start. You still got to get out of bed at some point. I got to be here at time, so it's 3 more Mondays. Well, I'm putting that thing in the drywall. It's scraped in the drywall. Funny, and now I got like tingles going. Ooh. You ever do that? It's like fingernails on a chalkboard or chewing on aluminum foil. Nobody ripped on purpose, but like if there's a little piece left on like some food or something, you in your mouth and you chew it, it hits you. Oh. Yes, it is. And everyone agrees with me though, so everybody knows. That's just bad.